Steiner, can you hear?
Yes, I can hear you.
Okay, the people are coming back, so we start in 2-3 minutes.
Okay.
Ну, сейчас.
Shall we give a talk? I'm sorry. I was shouting. Yeah.
Walter, if you're not speaking, please keep your channel muted. Steiner, there is some noise coming from your channel.
Is it okay now?
Yes, it was something like opening, closing, opening, closing.
Yeah, there was someone opening that door here.
Okay, very good.
You are ready.
Okay, I think yes. You can announce, yeah.
Okay, dear colleague, as we recognized earlier, challenges connected with continuation of boson-Higgs study, also connected with electron-positron collider. And in the heart of this collider is Click accelerator. We are happy that the first speaker, Dr. Steiner Calatroni, with us, but he will make a presentation with Skype, and you will explain what happened with the report and he already answered on our questions. So please.
Okay, Steiner, please go ahead.
Okay. So, first of all, can you hear me well?
Yes, we do.
Okay. So, thanks for inviting us to give a presentation about the Click accelerator activities at CERN. I'm connecting from CERN. Walter Wunsch is also connected. Walter Wunsch is working also at CERN, but he's in the US right now. And he knows more about the collaborations we've had with Ukraine in the Click project so far. So he will also be available to answer questions and comment if needed. So I will first give a general description of the Click project, and then I will move to say a little bit about the connections we've had with Ukraine groups in the past, and also maybe areas where we could imagine collaborating in the future. So first of all, Click is a study for our future linear collider, where the focus has always been to achieve the highest possible gradient to make a compact machine to go as high as possible in energy. So I will talk a little bit about the timeline of these studies, then the technical status, and then the plans for the upcoming period, 2020 to 25, before I summarize. Next slide, please. So here you see, first of all, the timeline for the project. We are now in an important phase because we have what is called the European strategy update for European update of the strategy for particle physics. So we are now putting together a project planning for an implementation of the CLIC accelerator. And then there will be a discussion about what to do in the next phase at CERN. For the CLIC project, we imagine that before we could start constructing such a machine, the goal will be to have the machine ready when LHC is completing its high Lumi program around 2035. We will need what is called a preparation phase, and I will talk a little bit of what we imagine we need to do during this preparation phase. So first of all, I will talk about a little bit about the technical status, which will go into the project plan. Next slide. In a very general way, any linear collider, there are two linear collider concepts being developed. There's the CLIC at CERN, there's the ILC, where CERN is also participating, but it's mainly pushed for a possible implementation in Japan. But then for both of them, the key elements are the same, and one has to create very low emittance beams, so well-behaved electron and positron beams. And then they are putting into damping rings to lower the emittance to the minimum. One is bringing these two electron and positron beams to the end. This is what is called RTML, ring to main linac. And then in the main linac, we try to accelerate as much as possible in the shortest possible distance. And for CLIC and ILC, one is using different concepts. For CLIC, we are using normal conducting structures, expand, so 12 gigahertz structures. For ILC, one is using superconducting RF structures. CLIC has put the goal to make this accelerator as compact as possible, and we are aiming now for a 380 GeV accelerator, which will be only 11 kilometers long. So it's a bit longer than the diameter of the LHC ring, but it's in fact it is quite compact. Then for both concepts, for any linear collider, one then has to go through a beam delivery system, BDS, to try to reduce the beam size to the minimum, because what goes into the luminosity of the machine are the emittances and the beta functions of the beams, and then one has a detector. Next slide. Here you see a map of a possible implementation of CLIC in 3 stages. So we are aiming for a first stage at 380 GeV, 11.4 kilometer. Then a second stage, which is still an open question because this depends on physics, around 1.5 GeV. And then we think the maximum we can go with this technology, given the geographical footprint in the area, is around 3 TeV, so 50 kilometer long machine. But most of the work now is related to the 380 GeV machine, because we know already with the discovery of the Higgs and the known mass scales of all the standard model particles, that the 380 GeV machine, we can do studies of the Higgs, we can do studies of the top quark, and all the other standard model particles in great detail. Next slide. This is quite a complicated slide, and I don't think I would like to go in very much detail on that. First of all, up in the right corner, there is a little film you can play, but I will not try to play that online. I think that's too risky. You can see the concept of the CLIC machine is, as I said, one has an injector. If you start in the yellow boxes at close to the bottom, you have an injector for electrons and positrons, and then a pre-damping ring and a damping rings for positrons and a damping ring for electrons. One transports these beams out, and then you accelerate them in the main linac towards the collision point into a beam delivery system. What is special for CLIC is that the most difficult things, in addition to having the high gradient, is to supply the RF power to this machine. And if you try to do that, even with a 380 GeV machine with normal classrooms and modulators, you need 2,000 to 5,000, depending on the implementation of these modules. So this is possible, but when we go to 3 TeV, it becomes impossible. There are just too many of these classrooms needed, and the lifetimes and the reliability of them will not make it possible. So one important concept of the click is to instead accelerate a very intense drive beam, which you see up in gray, up in the middle. So it's a very intense drive beam, and then we do a further combination of this drive beam into pulses, which we then distribute along the main linac. This is the red lines. And then we extract the energy of this drive beam into the main beam. This makes the RF distribution, RF creation and distribution much more efficient, because you can do it with longer pulse lengths, different frequency, and you do the combination, the frequency combination, and building up the intensity with beams where there's virtually no losses. And if you want to add another sector, you just make the pulse longer instead of increasing the power or changing in any other fundamental way. You just make the pulse longer, and then you have one more pulse you can distribute along the main beam. So this is illustrated in those two little figures on the right, where you see two structures, in fact, going parallel. You see the fat structure where the dry beam is going. You extract the energy of the dry beam and put it into the main beam. And below you see a module built in the laboratory to prove this concept. And we have also, I will show that later, we put such modules or such concept structures into a beam and proven that we indeed can extract the power and inject the power and get the acceleration we need. And as I said, if you run the film up in the left and the right corner, you will see a demonstration of how this is happening. Next slide, please. So the next slide just shows the key parameters of the 380 and the 3 TeV machine. The luminosities of which are in the range above 10 to the 34. The repetition frequency of these pulses, which are 50 Hertz. But these trains, each of them have 250 or around between 300 and 350 bunches. And inside the trains, the bunches are separated by half a nanosecond. And the gradient is given there for the 380 and the 3 TeV machines, and also the sight lane. As I said, for the 380 GeV machine, we could imagine to do this in a standardized way with a klystron and modulator, and this is shown in the diagram on the right. So we are looking in for the first stage of the machine to do it in a more regular way without the drive beam as a potential variation of the first stage of the machine. But when we go higher on energy, we have to go to the drive beam scheme to get the RF efficiency needed for such for reaching those energies. Okay, Maxime, now I move to the next topic. I will just show 3-4 slides about the main technical results we have. So if you go to the slide called 2-beam acceleration now.
Steiner,
yes.
I'm trying to follow up your slides with a laser pointer.
Yeah, so that's good. So we have at CERN a little test facility where we have build up a drive beam, not with a multiplication factor of 24, but with a multiplication factor of 8. And we have another, what we call a probe beam, which is representing the main linac. So we have proven that we can get well above 100 megavolt per meter with this type of method, extracting energy from a drive beam and putting into a main beam. And it's shown on the diagram below the main figure in the middle, where we see that for a given power into the accelerating structure, we reach gradients well above 100 megavolt per meter. So the limitation of the click accelerating gradients is not really coming from this method, We have shown that this method works, and we have also shown, even though I don't have the slide describing that the stability of this dry beam is sufficient for us to do the two beam acceleration. Next slide. The next slide is really in Walter's domain, but this is really the core technology development of CLIC. These are X-band 12 gigahertz normal conducting copper structures, and you see in the middle you see a little disc, and we put 24 or 26 of these discs together, and we create the accelerator structure, which is shown in the middle. And then we pulse these structures with the systems shown below. This we call them Xbox systems, to see that they can withstand the RF levels needed for us to operate at 100 megawatt per meter. And the relevant parameter is to look at the power we put into them, but also something called breakdown rate, which is arcing on the surface of these structures when you go to very high electrical fields. And this is an area where our Ukrainian collaborators have been very active to understand the different surfaces and what happens at the different surfaces for different electrical field and for different treatment of the copper in questions. So I will not go in detail on that figure, but what you should note on the axis below, what is called the unloaded accelerator gradient, is that we reach around 100 megawatt per meter for all of these structures. They have to be conditions, they have to be run for a certain amount of time before they reach this level. Along the other axis, the vertical axis, we have the breakdown rate, and we can see we can reach this breakdown rate at, the gradient at the breakdowns rate needed and with the pulse length needed. So these are the three parameters we have to optimize together. And this is really where the limitation for this is coming from. In principle, if we could put in higher electrical fields and more power into these structures in principle, even though the RF distribution in itself is difficult. But then we will have too many of these breakdowns. These breakdowns are not fundamental, but they do disturb the beam, and we have a criteria that we should not lose more than 1% of the luminosity in a 3 TeV machine due to this arcing, which have the potential of giving the beam a little kick. It doesn't have to do it, but it might do it. So we put a limitation from that type of criteria. Next slide. Well, the next slide shows different manufacturing techniques of these structures. So this is relevant for our optimizations of the structures, where we optimize the manufacturing, we optimize the production of them, so the precision needed, the surfaces, and we also look at different ways of putting together bonding versus bracing, or we also consider to produce them in halves instead of producing them in discs, which could reduce the costs. And next slide, I can go very quickly on, but it's just to prove that there are industries who can do this. They can produce all the different parts of the machine, and of course that's important for the credibility of making it possible to build such a machine. The next slide shows two other key parameters. The cost of a 380 GeV machine. We are updating this cost for the European strategy, and we are updating the power, which is shown on the right. The power consumption is in the end significant, and of course energy consumption is also cost in the end when you operate. But I will not go in great detail of that, but the main point here is that both the cost and the power are not very different from what LHC costed and what CERN is using of energy today on a yearly basis. So we think this machine is not controversial in terms of the resources required. Next slide is an example from Swissfall, which is in fact not running at 12 gigahertz, but running at 6 gigahertz. So it's a C-band LINAC, another frequency band. But it's interesting because you can see the structures. First of all, you see the nice Swiss forest and a LINAC there for a free electron laser LINAC. But you see below that, you see a structure made in C-band, which is necessarily a bit bigger because it's a lower frequency. But also you can see they are much longer, and they build them at very high precisions, as the Swiss like to do. And the mechanical parameters they have achieved is exactly what we need for click. So this is a proof of principle that such a machine is buildable also in practice of building many structures for it. And then finally, in terms of performance, one next slide, Maxime. To another key performance parameter, in addition to the energy, of course, and the gradient, is to make sure we have high luminosity. And this is quite complicated. We have to align the components of the machine over a significant distance. We have to control damp vibrations from the ground to the accelerator. We have to measure the beams extremely well because that helps us to steer the beam and optimize positions of elements. We need sophisticated algorithms for measurements of beam and components and the feedback between all these. And then we test all this in smaller accelerators. We test and facet at Stanford that we can preserve emittance, ATF at KK that we can produce the final focus parameters needed, CTF3, which is the machine I mentioned where we proved the two beam scheme, and then very light sources where light sources already produce emittances as we needed for click. So we try to put all this together to prove that we can reach the velocity we advertise for the machine. Okay, go 2 slides forward. In fact, 3 slides forward, Maxime, to come to a very blue slide. Yes, that one. So we are now thinking about what do we need to do in the next phase of the project. And again, I will not go into detail, but you see the main parts of the project. We have to continue developing modules as needed for click. And in fact, these modules are also very interesting for free electron lasers, where you can make very compact machines with this technology. We need to keep optimizing our structures. I mentioned producing them in halves. We have to work on high efficiency class transfer modulator, which is providing the RF either to the dry beam or to the main beam if we want to do it directly. We are developing magnets. We need a lot of magnets, not very powerful bending magnets, but very sophisticated quadrupoles and focusing magnets of various types. And we try to work with permanent magnets to get the power reduction down. And then it's all the practical and important issues related to civil engineering and infrastructure. So these are some of the key activities in the next phase of the project. Next slide. This is done as a collaboration, and the collaboration is a bit interesting. It's focused around click, preparing the click machine, but there has many of the collaborators now are using the same technology or planning to use the same technology for free electron lasers, varying from the large scale, so a 6 GeV machine, down to the very small compact machine you see at the bottom, where you have 50 to 100 MeV electron beam colliding with a laser and with Compton backscattering, becoming a mini light source, which you can use in-house. So this is a 5 to 10 meter machine, which is one could imagine to put in universities and in industries such that they can use investigations of material or biological sample or art or whatever they want to do with these type of machines. Next one, you see here a list of the institutes around the world which have this type of technology, and this is increasing all the time. Walter, who is listening, keeps a close eye on the development in all the different institutes around the world. And we also have a design study supported by the EU for using this X-band technology for free electron lasers. And of course, and next slide again. Let's see. This is we are thinking also, could we use this type of technology for a smaller machine, a CERN, for specific type of physics before we could implement a full click? And we have a series of studies now to which is called Beyond Collider Physics at CERN. And one idea is to produce a 3.5 GeV electron beam, which is a 70-meter long machine, so it's quite modest, and inject electrons into the SPS and extract them for searching for light dark matter. So this is in the case that dark matter is not the familiar things we've been looking for at LHC and LEP and Tevatron. It's not in the TeV, 100 to 200 GeV or higher range, but it's more in the GeV range. So, and this is a very interesting idea which many people are pursuing, and we have found that if we could get electrons into the SPS and extract them in a correct way, we can do this probably better than anywhere else in the world. So we are proposing this as a potential intermediate timescale machine at CERN using the X-band technology to make it cheap and compact. So this is another input to this European strategy. So this was a quick rush through the CLIC project. Then I will go talk a little bit about what we have been doing with the Ukraine group so far. And these slides are in fact produced by Walter. First of all, we have had a long-standing collaboration with SUMI, EIP SUMI, and this is related to X-band fundamentals in the sense, or what happens on the surface of copper structures and how can we optimize these copper structures. And this is experimental and a simulation, and there's also exchange of scientific personnel related to this. Next slide. So the issue there is that to test copper structures, I mentioned this Xbox systems, which pulse them at 50 hertz or 100 hertz and so on. But one could also imagine to pulse them much, much faster, smaller samples, and then learn from that how to optimize the materials, both what type of materials, but also how to prepare the copper for use in an accelerator structure. So there is a setup like that at CERN where we've had key collaboration help from SUMI to characterize that. And that's shown on the next slide. I think you need to. Is this the one called comparison of heat treated as mentioned?
Yes, it's comparison of heat treated.
Yeah, so this show the different type of soft copper and hard copper, and how by pulsing with this DC system very, very quickly can look at how the gradient develop, and you can see the difference in the two curves, or in the two set of curves, I should say. And we can also see that, for example, using hard copper, which is more tricky in a way when you put together the structures, much quicker get to the gradients we are interested in. So this is very, very interesting results, and it's very, very fundamental for us to understand as well, because it feeds directly back into how we produce the structure and how we specify these structures with industry, and how we actually produce them. So it's an example of fairly fundamental research on material science applied in particle physics. Then I have a completely different. And there, I think something has disappeared on the slide. This is an example, in fact, of oh, sorry, I'm mixing this up. Yeah, so this is another example of collaboration. But let's go to the next slide there, Maxime. So the the one after that. So another area where we've had the discussions for, in fact, for quite a long time. It goes back to 2013, 2014. We had a discussion with the groups in Krakow related to an EU application to support studies related to dielectric structures. This is now restarted in the sense we have a working group inside CLIC to look at could the CLIC machine at some point be upgraded, changed using plasma technology or new technology for acceleration. So this is a long-term development, which I will not discuss in any detail. And there are various ways of doing that. But one interesting way is to use dielectric structures. And in fact, we will have a presentation from the Krakow group on the 27th of June in our working group on compatibility between the CLIC machine and future technologies. And we also worked with Argonne in the US on this topic. And a CLIC machine with such structures in the future, either by replacing the technology I have or by adding this type of technology to go to higher energy. Of course, we can upgrade such a machine on linear collider by making it longer, but one can also imagine to upgrade them by changing the technology. So our collaboration with a group in Ukraine is very interesting for us in that respect. Next slide. This is a bit of a strange, well, I wouldn't say strange, but it's a more peripheral connection to Ukraine. We worked with a group in Hungary, in fact, who do measurements of magnetic fields, and the CLIC with two beams close together, the influence of one beam on another, and the influence of even variations of magnetic field, the Earth magnetic field, is something we have to take into account when we want to have small beams and long linacs. So we have a group in Hungary doing that, and in fact, they use an instrument developed by an institute in Ukraine, which I don't know. I just learned about this a few weeks ago, and when we prepared this, it came up that this maybe was worth mentioning. But there is an institute in Ukraine which seems to have a very specific knowledge about how to make this type of instrument for measurements of magnetic fields at a very low level. So they have very high signal to noise, low power consumptions, and so on, and very sensitive. And finally, one other area where I remember we discussed this in 2013 and 14, but we never followed it up. this is the idea of using an electron linac for neutron production, in fact, and I believe that has some interest in Ukraine, and we have other collaborators or other contacts there. We have in particular worked with a group in Tokyo where they have, and I gave you a link to a talk at one of the, what is called a high gradient workshop in 2015, where they look at this, and the idea is that, of course, if you can make this electron linac very compact, this could have eased the implementation of such an electron linac. And in fact, they're interested at the University of Tokyo because they even want to make this a transportable system, because they wanted to look at what happens in the Fukushima accident, and they wanted to move the electron linac up to look at the situation at the site after the accident. But they also have a facility at the University of Tokyo. So this is, and I remember we discussed this also with Jakov, if this would have an interest for future collaboration, but we never pursued it, and to my knowledge, we have not continued working on that. But maybe this is an area where we could consider future collaboration. Okay, so that brings me to the last slide. I go back to the CLIC collaboration. So we are preparing a project implementation plan for the European strategy. We focus on a 380 GeV beam CLIC implementation with dry beam as a baseline, but also looking at the clastrons to drive the beam. Both are upgradable. So we think this is a healthy project in the sense that we think it's technically sound, it's compact, it's financially realistic, and so on. And it covers the standard model physics very well. In the collaboration, and this is also an opportunity, I think, for groups in Ukraine, the technology is also a technology collaboration. So the technology has a spin-off to smaller systems, and from free electron lasers and other type of medical machines and so on, which I haven't talked about, but also that there it can have an impact to be able to go more compact, which could have so this is interesting for many of our collaborators, and in fact we get a lot of feedback from smaller projects among our collaborating groups. We now are planning for the next phase, and of course we'd be more than happy to include interest from Ukraine in our plans for the next phase. That's it. Thank you.
Yes, you can say, yeah. Yeah, thank you very much, Steiner, for this excellent presentation. So,
yes, it's Starishka speaking. I am chairman of this section. First of all, I congratulate the CERN with to be a successful operation, and also it seems that 100 MeV per meter we have in our pocket. That's right. Beside the very exciting application of the compact linear accelerator, I think we have considered new possibility connected with application of this linear accelerator for diagnostic. You see, the project, for example, as Thomas X in Orsay, give us 100 kV monochromatic X-ray. And it's very attractive for diagnostic using phase contrast idea. So I think within technology transfer program in CERN, it's necessary to consider this as a one very promising application. And now session is open for question. Do you have any question?
if you want to make a question, I think you should certainly use a microphone, because otherwise our remote speakers will not hear it.
No. Yes.
Giovanni, Steiner, there would be a question from auditorium, but just confirm that you can hear the question.
Hello?
Yes.
Can you hear me?
Steiner, can you hear?
I can hear, but I couldn't hear the question. I'm sorry.
Okay, I got it.
You have to speak very closely, or maybe Maxime, you repeat the question.
Yeah, I think Maxime, if you could repeat the question, that microphone at the front seems to be much better.
Yeah, so first of all, thanks for the beautiful presentation. A quick question about the development of plasma acceleration. My question is more on strategy, but I would like to have your view, because we are speaking about new accelerator facilities in a time scale which is 20 to 30 or maybe 40 years from now. So I wonder whether these new techniques can catch up and provide much more compact accelerators in this time scale.
Well, yeah, it's a good question. I think on the plasma acceleration, we see in a way a promising beginning of the gradients, at least for electrons and to some degree the positrons. I think where we are very far away, and I'm not even totally convinced there is a good solution, is to get decent luminosity out of accelerators at the energies we need, so 400 or 500 GeV or higher for that matter. Because if you look at the energy efficiency of these accelerators currently, their ability to produce and maintain low emittances, so to have many stages of these accelerators, I think we are very far away from what is needed for practical use for us. I think these accelerators, in fact, could well, as an example where I think these techniques will be used in industry and possible medicine a long time before we could imagine using them for our very demanding accelerators, because we need high energy, high luminosity, high reliability. So it's the worst possible situation for introducing a new accelerator concept. So I don't want to predict this. I think they are, as I said, they are many decades away from practical use in particle physics. But I think it would be a big mistake not to explore the possibility. Dielectric structures, I think, to me, it seems more intuitively easy to imagine using earlier than this pure plasma accelerations. Walter, I'm sure you can expand on that.
Yeah, I guess I would just take the opportunity, of course, the compatibility of linear collider technology, be it convention or plasma, is there's a certain flexibility, and if it's implemented as an upgrade. So I think we try to keep that option there.
More questions? No? Okay, so let's thank to Steiner and Walter again for joining us. Thank you very much we value very much your time and you stay with us, but we keep you for the next two talks, which will be related to click structure. So we will keep the microphone on so that at the end of the talks, you can ask questions if you would like, okay?
Okay, thank you.
Thank you.
Okay, thanks.
So we are in a hurry because we have a chance to lose the conference dinner. So I ask the next speaker to be shorter, and also because Dr. Steiner also explain main things connected with ambitious CLIC project. So next speaker, Dr. Vladimir Baturin, he will explain experimental results jointly provided with CERN.
Development of methods for increasing the stability of material of accelerator structure to highly vacuum electrical discharges in the click structures and experimental studies of the influence of an internal magnetic field on the probability of a high vacuum breakdown. Over the past year, CERN and the Institute of Applied Physics has built and operated a series of small high voltage systems or particle to main high gradient RF testing program for click. The main reasons are to provide perform to make experiments which test basic idea about material dynamics under high surface field. Compare materials, surface preparation, condition, strategies, and all. Simplified experimental conditions. The study were carried out of the accordance with the memorandum between CERN, CTF3 collaboration and the Institute of Applied Physics collaboration for the period 2017 or 2019 and are developed to research on the issues of materials for the manufacture of materials of the accelerating structure of the click collider and the development of technology for surface treatment of materials which would achieve the necessary value of accelerator gradients. Theoretical and experimental study of the effect of an external magnetic field on the probability of the occurrence of high vacuum breakdown. These studies during 2016 or 2017 was conducted on experimental stand at CERN, Yaroslava Profotilova, and the Institute of Applied Physics. In the Institute of Applied Physics, ion beam and plasma modification of the surface layers of materials were carried out to increase to stability of structural materials of the accelerating structures to high voltage breakdown, and the effect of such modification on the field emission current and gradients of high voltage and high vacuum breakdown were studied. At CERN, high voltage conditioning of materials for accelerating structures and was investigated, and the probability of high voltage breakdown. Investigation of influence of an external magnetic field on high voltage breakdown was carried out independently at CERN and Institute of Applied Physics. The CERN DC Spark system, first installation contained a plain cathode and tip anode, and the next installation is large area electrodes installed. Experiments on the condition for different materials in CERN. Experimental experiments with carry out on large electrodes installation. This slide shown a comparison of the conditioning process for various materials: hard copper, soft copper, niobium, et al. Experiments were carried out of installation at constant voltage. The conditioning copper with has undergone only machining occurs more quickly and with greater electric field value than copper, which has undergone additional thermal treatment. The Institute of Applied Physics DC Spark system. This slide shown in the schema and the picture of the our installation. In our installation, constant contained a plain electrode and a tip anode. The cathode typically 12 millimeter diameter disc sample. Tip and anode 1 millimeter radius hemispherical tip. Gap typically 15 or 100 micrometer. Before measuring the vacuum chamber is heated during the one day. The vacuum in the measuring process was 10 in the -9 degree millibar. The DC voltage between the anode cathode varied from 10 and 100 kilovolt. The mass spectrometer made it possible to measure the mass spectrum of gas in the vacuum chamber. The ion current anode cathode is measured with accuracy on 1 nanoampere. Three main types of the copper samples were used. Surface cleaning, polishing, annealing cleaning, glow discharge, and samples iron plasma coating titanium films, coating TN films, coating molybdenum films, and samples with iron implantation treatment with argon 2+, zirconium 2+, nitrogen 2+ ions. Part of the copper samples passed the following procedure: polishing, heating in high vacuum, and cleaning in the glow discharge on argon plasma. Fig 1 shows the histogram of a breakdown voltage and the dependence of the dark current between the anode cathode, Fig 2. For copper samples with different surface treatment, vacuum is 10 in minus 7th degree Pascal. Annealing at 33,015 degree increases the breakdown voltage by 10%, and glow discharge cleaning 20%. In this slide, shown total histogram of breakdown voltage for copper samples with different surface treatment. Copper plus titanium film, copper plus argon 2 plus irradiation, and other. Copper samples with coating. Coating on the copper surface, the deposit by the methods of magnetron sputtering. Coating with molybdenum or titanium films increase the breakdown voltage by 60 and titanium TN by 25%. On the surface of copper samples, various defects can be center of electron emission and stimulate discharge. It can be different inclusion on the surface of the electrodes, gained boundaries, surface defect obtained during its manufacture. In his case, the titanium nitride film smooth and fills surface defect. Thin titanium nitride films on the copper surface can behave as a barrier to the diffusion gas from the cathode volume. In the study of the anode was made in tungsten. Copper samples with ion beam treatment. Irradiation by argon 2 plus, nitrogen 2 plus, zirconium 2 plus with energy 300 keV. The irradiation with argon 2 plus and or nitrogen 2 plus ions of pure copper and coated copper samples lightly, approximately 10% affects the breakdown voltage. irradiation of copper samples and samples with titanium nitride films or argon plus ion leads to the increase of the breakdown voltage. In this related to the effects of the displacement of dissolved gas from the surface layer by argon ions and smoothing of surface defect. The best results increase breakdown voltage, approximately 35% was obtained on copper with titanium nitride coating and additional irradiation with argon plus. A theoretical study of effect on magnetic field on field emission. The equation for Fowler-Nordheim with relativistic case was obtained. Next, experimental studies of the effect of magnetic field of high voltage breakdown where magnetic field perpendicular is electric field. The experiments at CERN were carried out on installation with large electrodes facility. The magnetic field perpendicular to the electric field does not affect of probability of breakdown. And EPF experiment experimental performed at the Institute of Applied Physics has shown that the used the magnetic field leads to an increase of a dark current of anode, cathode, and decrease of the value of breakdown voltage on 10-20% for the all copper samples, regardless of the surface modification. Conclusion and future plans. The next project is planned to continue these studies, in particular to determine in more detail the optimal value of the thickness of the coating and the dose on the irradiation. It is also important to focus on the measurement of dark current and its dependence on the type of coating and the dose on ion irradiation. It is also important to investigate the dependence of the breakdown voltage and the dark current from the distance between the electrodes. And ion plasma modification of large copper samples will be carried out for joint research at the CERN facility. Thanks.
Yes, thank you very much. So, do you have any question? Well, no questions.
Perhaps I may make just a comment.
Yes.
It's very interesting results, and very promising results. And I think the next step on our side would also be to reproduce them in the setup at CERN. So we look forward to planning that next activity as well. Thank you.
Yes, thank you very much, Dr.
Я переведу.
Переведите.
Walter, I will be translating. Да.
Что он спросил, я не очень понял. It's okay.
Okay, so we misunderstood you. I'm sorry I wasn't here, so it was a statement and not a question. We were expecting a question from you. Okay.
Yes.
Okay, let's thank the speaker again.
Okay. So we are in a hurry. So next speaker is Dr. Anishenko, development of the multi-bunch dielectric wake field accelerator conception. But it seems that there is replacement. Again, I asked you to be shorter.
Can you hear us, Steiner, Walter? Hello?
Yes, it's
okay. Very good. We are just checking because we are not sure. Okay, very good.
I am not Dr. Anishenko. I am not Dr. Anishenko. I am Dr. Sotnikov. On behalf of Dr. Anishenko, I will talk about wake field acceleration in electric structures and multi-bunch regime. These studies were carried out in Krakow Institute of Physics and Technology. Motivation of this study are the next, that energy frontier of particle physics requires energies of order TV energy range. But colliders capable of reaching this regime, such as Large Hadron Collider or International Linear Collider, or click about this scheme was reported in the first presentation of our session. These devices are very costly and time-consuming to build. You can see that compact linear collider is planned to finish in 2035, after 20 years. Therefore, it is important to explore new methods of acceleration particles to reach high energies. Future colliders will be based on, I am sure, will be based on an advanced method of acceleration. Among them, laser plasma wake field acceleration, laser beam plasma wake field acceleration, beam dielectric wake field acceleration. The best results now experimentally obtained for the laser wake field acceleration, where accelerated gradient about 100 GeV per meter is obtained in Berkeley National Laboratory in Texas University. And a scheme of plasma wake field acceleration is obtained at accelerated gradient about 50 GeV per meter at slug. And dielectric wake field acceleration now is obtained at accelerated gradient experimentally up to 3 GeV per meter at slug. For comparison, you remember that click will provide 100 MeV per meter, or International Linear Collider will be provide 30 MeV per meter. Dielectric wave field acceleration is based on Cherenkov radiation of bunch in dielectric slowdown structure, and the accelerated gradient is proportional bunch charge and inverse proportional square of vacuum channel. And wavelength is proportional to 4 thickness of the electric layer. The studies about ice, will say, are carried out in framework of execution STCU project P 5222 with collaboration Argonne National Laboratory. Experimental installation for what we carried out our experimental investigation shown here, and it provide next parameters of beam energy of electrons from 2 to 4.5 MeV, pulse current up to 1 ampere, duration of wave pulse 2 microsecond, bunch repetition rate about 2.8 gigahertz. Number bunches we can change from 300 to 6,000. Each bunch charge about 0.32 nanocoulombs. Bunch length 1.7 centimeter, and bunch diameter 1 centimeter. Below you can see an example of the slowdown structures equipped to accelerated, and a rectangular example of our dielectric unit. At first, I will say about wave field excitation in dielectric waveguide by sequence of relativistic electron bunches. Under dielectric waveguide, I mean dielectric structure without any reflection at output end. What is the problem of this statement? It is before we have shown that Cherenkov radiation train behind bunch, the waveguide exit is limited some length. Its Cherenkov train is proportional to length of the electric structure, and difference between group velocity and phase velocity, or velocity of beam. Therefore, now due to removal of wave field from waveguide exit with group velocity, maximal number of functions wave field, summation of which leads to total wave field increase, is restricted this number. Therefore, varying the length of the electric waveguide allows to observe wave field at the exit from various number of bunches. Thus, instead of changing the length of resonant sequence of bunches, that is difficult to realize in experiments, we vary the length of the electric waveguide. It can fill separate bunch. Before experimental measurements, we have studied particle cell simulation of this device. You can see this geometry of simulation, and it consists of the electric tube in the vacuum part, where we can place diagnostic devices. At the right, you can see dependence of excited axial longitudinal wave field from length of the electric tube. You can see that it increases with increasing of length of the electric tube and oscillators. Vertical guide lines are drawn for each half length of the lowest resonance value. Maxima is located when length of the electric structure is multiple to half wavelength of my principal mode. Experimental study result of experimental studies are shown in this slide. This is measurement were made for non-matched device and matched device. This installation consists of accelerator, almost 2 energy analyzer, dielectric tube, dielectric plug, and measurement devices. In comparison with non-matched case, there is cone, dielectric cone, and horn, and ferrite absorber. Best result we obtained for the matched case, and these results are in good agreement with theoretical prediction. The second studies were made for dielectric resonator, and under the dielectric resonator, I mean dielectric structure with short-circuited input and output ends. The used resonator eliminates the effect of removal of wake field from the structure, and the optimal condition excitation of the electric resonator by a sequence of bunches is similar to excitation of optical resonator by modulated laser equipped with optical switch. At the moment when short pulse of radiation reflected from output end of resonator appears in the input, the optical switch injects the next pulse of resonator. For the coherent addition of excited fields in the electric wave field resonator, 2 conditions must be fulfilled. The length of resonator should be multiple to 1/2 of a resonator wavelength. And the second condition, a bunch repetition frequency must be equal to resonance agent frequency of the electric structure, or resonant agent frequency are multiple to bunch repetition frequency in multimode regime. Planar example of increasing excited wave field in the resonator is shown in this structure. Parameters for the computation were chosen the same as the experimental installation. In the left, you can see excited wave field after injection 5 bunches. Excited gradient is 3 kV per centimeter, and after injection of 100 bunches, excited wave field is equal 60 kV per centimeter. Thus, you can see accumulation of excited wave field in the resonator. A more realistic case is shown for this slide. We have computed excitation of dielectric resonator with additional vacuum part, and the left pictures are shown again frequency of this resonator, and the right pictures are shown axial longitudinal wave field in the electric part and vacuum part, and the right figure transverse electric field. This here is shown the best result of wave field excitation when the length of vacuum part is equal 1/2 of the length of vacuum part. For testing of this prediction, we have made experimental measurement of excited wave field in resonator statement. In comparison with previous installation, we have the electric plug to support vacuum in the dielectric unit, and a short circuit plunger in order to change vacuum path of a resonator. At the right figure, you can see the dependence of longitudinal electric field from length of vacuum path of resonator. You can see very peaked maxima at the length of resonator multiplied to 1/2 wavelength of vacuum path. In this case, we obtain accelerated wake field 24 kV per centimeter. That allows us to obtain accelerated field inside of the electric part. That is equal about 12 kV per centimeter. Dependence of wake field amplitude of number injected bunches into resonator is measurement is shown here. This accelerogram show beam current, red line, and microwave signal for the three cases or different with number of injected bunches. The first 300 bunches, 900 bunches, about 4,000 of bunches. You can see that with injecting additional bunches, excited wake field increases. We also studied dependence of excited wake field from Q factor of resonator. This is shown in this slide for a different Q. Very low, very bad resonator 65 Q, and last example, relatively good resonator 670 high. We also studied acceleration in this structure. Example of acceleration is shown in the right slide. In these studies, we have obtained acceleration of bunches about 150 kV. At the last studies of plasma dielectric wave field accelerator, focusing on driving accelerated bunches. Also, dielectric wave field accelerator has less accelerated field in comparison with other advanced schemes, PBFA or LFA. It can be considered as a promising candidate for fusion electron-positron TV colliders. But there is one shortcoming. It is suffering of beam breakup instability. Also, it is total shortcoming for all linear accelerator. In comparison with traditional scheme of suppressed BBU instability, we proposed to use for focus on drive witness bunch to fill the drift channel with a plasma of certain density. Also, plasma filling can increase accelerated gradient. In this, our idea is demonstrated in this slide, where is shown axial electric field accelerated gradient and focusing electric field. You can see that drive bunch, yellow rectangle, and accelerated bunch are in focusing phase of total wake field. For the experimental investigation of acceleration and the focus in electron by wake fields inhibit plasma dielectric structure, we used this installation in comparison with previous scheme we have vacuum pump for pumping neutral gas in the unit, and for diagnostic of focusing, we have double Faraday cup with different diameters, with different holes, and that allows to measure passing current. Focusing of drive bunching is demonstrated in this slide. Left picture show beam current at first cup, and red line and blue line the second cup. In the case of very low pressure of neutral gas. When we fill vacuum channel with a plasma, beam current on first cup decreases, and beam current to the second cup decreases. Therefore, we in this experimental measurement, we have obtained focusing drive bunch approximately by 2 times. I cannot do conclusion. I say about further studies of our dielectric wake field acceleration. It is rising problem of wake field acceleration, wakes in long tubes, directed measurement of accelerating fields, measurement of transformer rational that is play a great role in acceleration. It is very important for multi-zone two-channel drive and Vitas channel dielectric accelerators. Metallization of ceramic structures of dielectric wave field accelerator. No need to use metal waveguard. And studies dielectric structure charging, dielectric fatigue, sub-breakdown fields, change of dielectric properties under the influence of electron irradiation. That's all. Thank you.
Thank you very much. Does somebody have a question?
We will ask. Steiner, Walter, do you have some questions?
Very, very interesting. It will be interesting also to see the slides. It was a bit difficult with the video connection.
Okay.
We definitely are very interested in this kind of work. Just a comment, of course, when comparing gradients, these pulses tend to be rather short compared to the relatively longer normal conducting and superconducting pulses. So when quoting gradients, but I think we will look forward to discussing these subjects in the coming weeks. So
Okay.
Thank you.
Okay, so what I will do, I will pick up the slides and send to both of you by mail. Your slides to send to them.
Okay.
To provide them the slides,
okay.
yes, exactly.
Thank you. I will send you.
Yeah, we can do it.
Okay.
Okay.
Thank you.
Okay.
Do you have anybody question?
Okay, if no other questions, thank you so much, Steiner, Walter, that you joined us. We would still have a talk on the time projection chamber for the International Linear Collider as a last talk. So if you're interested, you are very welcome to stay, but if your time commitment requires you to leave, I mean, we perfectly understand the situation. Okay.
Yes. Any question? No. I just want to make some comments.
Microphone, so that the people.
Exciting talk. I am very glad that this direction is still alive in Kharkov Physical Technical Institute. But of course, there are many questions concerning quality of the beam, which is extremely important for many applications. And also, I just advise, don't consider this technique as alternative technique to click technique, because click facility is based on very mature technology, very well-recognized technology. So I think the research in this field is extremely important. And I hope that it's a good chance for collaboration with CERN. Yes.
I want to say that the scheme about I said belong to beam accelerator scheme. More advanced, but it is to beam acceleration scheme.
I am very old, and I remember that 50 years ago, Professor Sarantsev in Dubna promised to build this accelerator. Yes, but you see, situation is very complicated. So supporting this very exciting idea, don't close the alternative, very mature technology and very recognized technology. It's just advice.
Thank you for your comment.
Okay. So,
thank you very much. So we have chance to listen Dr. Last presentation, Dr. Sheikha from Kyiv State University. Please. Again, I ask to be shorter.
Что в корне? Угу. Хорошо. Что прямо с этого запустим?
Good evening, everybody. Sorry, I'm late. I will try very shortly, but it's very difficult. A few minutes. It's my presentation is very short presentation about our status, about our work of our team. Nuclear physics department, Kyiv University, Taras Shevchenko, Kyiv University, National Kyiv University, and in the frame of the LCTPC collaboration, ILD detector concept group. LCTP collaboration for the International Linear Collider, ILC, 3 concept studies for detectors, and the main parts of ILD, one of conception ILD detectors, TPC, time projection chamber, LCTPC collaboration is directed on this development of this TPC on the new base. You can see some schemes. It's not for TPC in the ILD concept group. 2 parts. ILD combines excellent tracking due to TPC, and finally grain calorimetry systems. This gives ILD ability of reconstruct the energy individual particles. non-particle flow approach. Very simple for time projection chamber. Time is short, and I think, work of time projection chamber. The main using of old such systems 2D plane was ultimate wire drift chambers. Last years, these wire drift chambers changed by more perfect systems on the base of GEM or micro-mega systems or INGRED micro-pattern gases detectors. Some examples of these systems you can see here. LCTPC work in this direction: small prototypes, large prototypes, and design. Now, large prototype, this stage of this collaboration. We also work in our directions in the scientific work in this frame. Development of the test tool LITEH on the base of electron linear accelerator field in the LAL also. Study of MPGD panels as part of LD detector at the LITEH, and development of the test facility on the nuclear physics department to characterize and study MPGD. Various, but in the micro pattern gas detector, various types, but first of all, INGRED detectors. Whole work is performed in cooperation with LAL and IRFU from France. I am grateful for invaluable assistance to dual participants, Larissa and Konstantin, and I have two names, sorry for time, our large number of our students who took part and take part this work. Alexey Fedorchuk, Volodymyr Rodin, Nikita Garanko, Danil Sukhanov, Vladimir Krylov, all these students now PhD students in various countries and various institutes. Now Vladislav Krylov now is PhD student of our university in cooperation of French LAL laboratory institute and university Paris Sud. In main part of this work of your work, part of this presentation. LITEH, the simple separator of electrons on energy, and these electrons has very good characteristics, such characteristics in the simulation, just for up to 1% of energy resolution, and in time resolution a few picoseconds. You can see our work from Jan simulation, development, construction, design. Magnet was produced in CERN. Other parts were produced in our department with students from electronics, mechanical parts, and other all the parts. And you can see design, production, and commission of this system. After that, after commission of system and test on the simple detectors, we use first our large using of the system was measurements using grid peaks module, large module of 96 chips, INGRED chips. From Bonn University. You can see large module, this module, and after in experiment, we obtained tracks on this model in parallel plane. After Vlad Krylov wrote a special program for semi-automatic track analysis, and now he work in the direction of analysis of power stopping power in the various gases and others. Also, we study now to study track reconstruction using hardware chips for acceleration of calculation first steps, using FPGA, SOX, and SOX plus GPU and new systems, artificial intelligence hardware chips. For example, you can see Movidius Myriad X, the new direction is very interesting, especially for students, and promising direction. For example, our test facility in the main part of this work for us, for our students, was to build and develop a facility in our department. Now we are working in these directions, our students, and we learn to use special tools such as Garfield++ and others. You can see first results, simulations. These packages for this is simulation geometry electric field micro TPC in RFU. And for example, simulation task for octoboard, 8 chips on this one octoboard, and you can see some problems for this octoboard in simulation system. And now we are building test facility in nuclear physics department. Main paths are we have main paths of the system. Now we work on the readout part of for micro TPC. You can see, for example, work of our young people who made micro TPC using 3D printer, and now the students are working on the readout part. Conclusions, same as part of my presentation, and yeah, shortly, I think I finished.
Thank you very much. Do you have any questions? Comments? No. Okay.
So I think this ends the first day program, and I think our hosts can tell us, Andrei.
Yes, we now collect here in our hall, and all